Welcome to BC Video 10.3a Part 3, End of the Calculus of Parametric Equations.
29 to 38, find all points, and those points will be in xy form, if any, of horizontal and vertical tangency to the curve. Use the TI to confirm. Remember, the slope of the tangent line is dy dx, which makes it dy dt over dx dt. So here's an example of a set of parametric equations. They want the horizontal and vertical tangents to the curve. So horizontal would mean the slope of the tangent line is 0, which would mean dy dx is 0, and rare that dx dt would not be 0, right? Because dy dx is dy dt over dx dt, and you couldn't have a dx dt of 0. A vertical tangent line, of course, the slope is undefined. So dy dx is undefined, which would mean that dx dt is 0 because dy dx is dy dt over dx dt. So we're going to need to find dy dx, which is dy dt over dx dt. From y, we find dy dx is 2t plus 3. From x equals, we find dx dt is 1. So we simplify that as our horizontal. That is our slope of our tangent line. So if it's going to be a horizontal tangent line, we're going to need that derivative to be 0. So we take 2t plus 3 equal to 0. We get t equals negative 3 halves. But they are looking for points, and those points have to be in xy comma. So now what you do is you take your t equals negative 3 halves and plug it into your original set of parametric equations. And that gives you negative a half comma negative a quarter. When does it have a vertical tangent line? Well, it has a vertical tangent line when the slope is undefined, which is when 2t plus 3 is undefined, and of course there is no number that's going to make 2t plus 3 undefined. Okay, from the graph you'll be able to observe that there seems to be a horizontal tangent line at that point. And do be careful that you don't leave the t min as 0 and the t max is 6.28, because if you left it, the t min at 0, this is all you'd see. You need the t min to be quite low. And again, this is how you would do dy dt over dx dt after you've entered your parametric equations. Okay, so remembering from arc length, rectangular arc length, if you remember from section 7.4 not very long ago, the arc length is the integral from a to b of the square root of 1 plus f prime of x all squared dx. And that's the arc length on the graph of f of x from x equals a to x equals b. So again, you're going to go through that whole proof. Maybe you remember this aspect right here, but here's how it's going to play into parametric. Okay, so parametric arc length, x equals f of t, y equals g of t, a set of parametric equations, and they want the arc length from t equals t1 to t equals t2. So it's a slight adjustment to the formula. It's still arc length. It's going to go from t1 to t2. And remember up here, our arc length was the square root of 1 plus the square of the derivative. Well, I worked through it. If you work through that using the same process, and I'm not going to sit here and actually do that, but at one point during this proof you had this, which is of course exactly what this is, which is dx, the square root of dx dt all squared plus the square of dy dt. And again, it should look familiar. It's a distance formula, square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, on the TI Inspire CX cast, for arc length, all you can do is for a rectangular arc length. It doesn't have anything for parametric arc length. But if you do want to do rectangular arc length, you could go to the catalog and select arc length of whatever your function is, comma your variable x from start to finish. You could also use f1 of x for the expression. Or in calculator mode, you could go to menu, calculus, and arc length. Okay, so let's say they give you this set of parametric equations and they want the arc length from -1 to 0. So here's our formula. We're going to need dx dt. dx dt will be 2t. We're going to need dy dt, which will be 12t squared. You're going to square them both, and you will get the following. Now we're going to just look at that and see what we can do with 4t squared plus 142t plus, 144t to the fourth. So we're going to factor out the 4t squared. We'll have this. Then the square root of 4 is 2. The square root of t squared would normally be absolute value of t. But if you remember, the absolute value of t is t if t is positive or 0, and negative t if t is negative. Well, t is negative here because it's between 0 and -1. So to get rid of that absolute value, once we take the square root of t squared, it's not t. This is a bit tricky. It is negative t. Now I'm going to let u equal the contents of my radical. My derivative will be 72t dt. I've already got 2t dt. I just need to introduce a 36 counteract with a 1 over 36. And now I can pull out, this is my du right here. Okay, but I need to pull out the negative because my du didn't have a negative in it. So I pull the negative out, 1 over 36, integral of u to the half du. Well, when you integrate u to the half, you get u to the 3/2 over 3/2. And then we're going to replace u by what it's equal to, which is 1 plus 36t squared. And keep in mind, originally it went from t equals -1 to t equals 0. So that's what we're going to do. We're going to take that expression and replace the t's by 0 first. So when I replace it by 0, this whole thing is 0. 1 to any power is 1. I just left this factored on the outside. When I plug in the -1, this will become 37 to the 3/2. And that's as far as you could go without a calculator.